Questions to hear? I don't think I've taken a break for questions yet, so questions to hear? Yep. We used the terminology out in the hallway about the fact that energy was basically getting burned up or something along those lines. Friction was transferring energy from the coil into the floor. So the floor probably heated up just a little bit, warmed up a little bit. But it's sort of implied in that is that there was energy in the wave, so let's take a look at that. So first, let's just think about something in simple harmonic motion. Because again, we're modeling on the idea is that this point right here at the peak of a wave before is basically undergoing simple harmonic motion. It's at rest, it speeds up, it slows down, stops, goes back in the other direction, just repeats over and over again. So I have something compressed on a spring. It's going to oscillate back and forth. I know that the energy exerted by the spring here is a conservative force, and so energy is conserved. So energy is a constant. And what are the two types of energy involved? Question to you, what are the two types of energy involved?
Potential and kinetic.
Yep. So I have kinetic plus potential. So at any moment in time, if I take the kinetic and the potential, I add them together, I get my total energy. And so if I can identify one spot, I have it for all of it. So this would also be equal to whatever the maximum kinetic energy is, which should be equal to the maximum potential energy if U min is equal to 0 joules. So my maximum amount of energy is 1/2 mv max squared. At this point, I need to hit no so I don't go in a circle. So we have this idea of this maximum speed, except we're not really measuring the speed. I know the maximum should happen while it's going through the middle section. So when this piece of the wave hits here, that should be its maximum speed. Let's think back to the equations for simple harmonic motion. I had a position with respect to time, which is some amplitude times the cosine of omega t. Sure, plus phi. My velocity, what is my velocity equation? If I can use this as a description of my position, what is my velocity?
It's going to flip the sign, negative sign.
All right.
It's going to be A WT plus theta.
Close.
Plus phi.
All right, so it's going to be, there's a plus phi there.
2 AW. Something.
What is that letter, by the way? It's not a W.
Yeah.
It's omega.
There we go, it's an omega. So omega t plus phi in there, and out front, A omega.
There you go.
Yeah. I think you pretty much said it in pieces, if not all together. So this is my amplitude right here. So my amplitude of my speed, well, that's my maximum speed, is just A times the omega. So whatever my amplitude is times omega. So I can now take my equation here, and that's 1/2 times the mass times A omega squared. Except that if I'm oscillating this thing back and forth, and even when I wrote the equations over here for the speed of the wave, I didn't use omega, I used frequency, I used F. What's the relationship between omega and frequency? Or the relationship between angular frequency and frequency? Someone's about to share.
Are they equal?
Yep.
No.
The frequency of our electrical current is 60 hertz, but the angular frequency is about 370 something hertz. Sorry, radians per second. Pardon?
What was the original question?
What's the relationship between frequency and angular frequency?
Angular frequency is equal to 2 pi times frequency.
So this now, we got this 2 pi f stuffed into here. And I'm gonna square all of that, so I got 1/2 times mass times 4 pi squared a squared f squared. That 2 cancels out with part of that. So we now have a formula for the energy of a wave. So that's equal to 2 pi squared m a squared times the frequency squared. But it doesn't really make sense when I'm talking about an entire string and I have a pulse only in one small part of it. So like when I had the coils, I just did a pulse, watch that go down and come back. So we can come up with something a little bit more flexible. If I look in terms of linear density, which is just mass over length, or the mass is the linear density times the length. So plugging that in there, we have energy is equal to 2 pi squared mu L a squared f squared. And then putting it into the form that the book has, the energy per unit length. Energy per unit length. I guess I'm blocking Selena there, sorry. Energy per unit length is equal to 2 pi squared mu a squared f squared. Let's think about this. There's certain parts of this that completely make sense. When I increased the frequency out there, what did I have to do to increase the frequency of the coil?
You had to move faster.
So it takes more energy out of me in order to increase the frequency, so that energy is going somewhere, it's going into the spring. So as the frequency increases, the energy increases. Amplitude, what do I have to do to make a bigger amplitude? If I'm moving further, I'm putting more work into it, that energy's gotta go somewhere, it goes into the coil out there, or a string, or whatever it happens to be. So as the frequency or the amplitude increase, the energy per unit length also increases.
So both of those, it increases exponentially. Like the energy will increase exponentially.
Are you commenting on the fact that it's squared?
Yes.
Technically, that's not exponential growth. Exponential growth would be if the variable were up at the exponent. So, and the fact that it's squared is, I think, falls out of the mathematics. Sorry, I think I missed your point. Do it. You were just making a comment about it, or you were looking for some rationalization without the math?
Yes,
Okay,
that one.
yeah, I'm not sure I have a rationalization without the math.
Like, it,
You got one?
yeah, the more, hang on. What is the mu there for?
When I took mass out, I substituted in UL.
Yeah, okay, so, I guess just like in kinetic energy, the faster, something goes, the more energy it has.
True, squared. I mean,
Yeah,
that's
squared, right.
that's why it is squared, just because that was the speed squared.
And, I suppose the energy matters, or the velocity, not the velocity. I know the frequency matters more than the mass, per se.
I mean, clearly it does from the math here, and I'm stuck in the math at this point.
I don't know how to differentiate that from, or like to take that away from the math, or from the math, but.
Yeah, I don't know either. But if you got it clear in your head,
Yeah,
that works for me.
it works fine in my head, yeah.
Okay. Well, as Nick is making it clear, it's time to go.
So really you
I'm not
sub,
trying to be rude, I
No,
got.
no, I understand. No, well, time's up, people have to go.
so what you're doing is substituting the mass for mu.
Well, it's mu times L.
Yeah, mu times L is mass.
Yeah.
That's the same as mass,
Yes. Yes.
theoretically.
Well, by definition
Yeah.
of linear density, so that,
Okay. They got too many letters for me.
there's a certain alphabet soup nature to it.